Chapter 1: Matrices and Transformations. So far, we know 4 types of transformations: reflections, rotations, translations, and enlargements. A reflection is a transformation that flips a shape over to create a mirror image. In a reflection, the object and its image are the same size and shape, but are laterally inverted with respect to each other. The dotted line of reflection is called the mirror line. It is sometimes called the axis of reflection. Under a reflection, 2 corresponding points are equidistant from the mirror line. A reflection is described by the equation of the mirror line. A rotation is a transformation that turns a shape through a certain angle about a fixed point. In this example, the figure was rotated anti-clockwise. In a rotation, the object and its image are the same size and shape. The point about which a shape is turned is called the center of rotation. A rotation is fully described by the center and angle of rotation. A translation is a transformation that moves or slides a shape through a given distance in a given direction. Under a translation, all points on the image move through the same distance and in the same direction. The size, shape, and orientation of the object is not changed under a translation. Therefore, points on the object can be joined to corresponding points on the image by a set of straight lines which are equal and parallel. A translation is fully described by a vector because it has both magnitude and direction. In this example, each point was moved 9 places to the right and 4 places upwards, so the translation vector is 9, 4. An enlargement is a transformation that increases or decreases the size of a shape. The sizes of the sides of the shape increase proportionately. In this example, the image is twice the size of the object. Each side on the image is twice the size of the corresponding side on the object. The angles, however, do not change. We say the object has been enlarged by a scale factor of 2. If you join the corresponding points on the image and object, they intersect at a point. This is the center of enlargement. An enlargement is fully described by the center of enlargement and the scale factor. In this chapter, we look at 2 more transformations: shears and stretches. We start with shears. Now, consider this pile of books on a table forming a 3D shape of a cuboid. If the pile was pushed carefully in this direction, the shape appears more of a parallelogram. Notice that the lowest book in contact with the table does not move, and that is because the table did not move. The top of the table is said to be invariant, and the book in contact with it is invariant as well. Notice that the direction of displacement is parallel to the invariant table surface. This kind of a transformation is called a shear, a transformation that keeps one line invariant and all the other points move parallel to the invariant line. The topmost book moved the longest distance, or it was most displaced, and that the bottom one was displaced the least distance, that is 0. The topmost book is farthest from the invariant line and thus moved the farthest than the rest. In a shear, the distance moved by each point is proportional to its distance from the invariant line. The constant of proportionality in this relationship is called the shear factor. Let's call it S. S is equal to distance moved by a point over the perpendicular distance of the point from the invariant line. We can make that simpler by saying S is equal to displacement over the perpendicular distance. Given the shear factor and the perpendicular distance, you can find the displacement by simple cross multiplication. Displacement is equal to the shear factor times the perpendicular distance. Always remember, it's perpendicular distance from the invariant line, and displacement is always parallel to the invariant line. When the s is positive, displacement is to the right or upwards. And when it's negative, displacement is to the left or downwards, depending on the invariant line. For example, we have triangle ABC and we want to get its image under a shear factor 3 with y is equal to 1, the invariant line. Two things to remember. 1. Points B and C lie on the invariant line, and so they don't change. Only point A will change. Number 2. The shear factor is a positive, so displacement is to the right. Remember, it has to be parallel to the invariant line. So how much will A be displaced? Perpendicular distance from the invariant line is 2 units. S is 3, and so displacement is equal to 2 times 3, which is 6. So it has to be displaced 6 units to the right. 1, 2, 3, 4, 5, 6. This is our new A prime. B and C don't change, and so we have triangle A prime BC as the image. If the shear factor was, say, -4, then displacement will be equal to 2 times -4, which is equal to -8. And so that is a displacement of 8 units leftwards. So 1, 2, 3, 4, 5, 6, 7, 8. So that would be the new figure. What if only one point lie on the invariant line? We have triangle PQR undergoing a shear with a shear factor 3, y is equal to 1 invariant. Point Q lie on the invariant line, so it does not change. P and R will be displaced, but by how much? Let's start with P. Perpendicular distance from the invariant line is 2 units. S is equal to 3. Displacement is equal to 2 times 3, which is 6 units to the right. 1, 2, 3, 4, 5, 6. This is P prime. Point R. Perpendicular distance from the invariant line is 1 unit. S is 3, so displacement will be equal to 1 times 3, that is 3 units to the right. So 1, 2, 3. Joining the 3 points, this is the figure we obtain. If the shear factor was a negative, we will displace the points leftwards. What if no point lie on the invariant line? All of the points will be displaced. We have triangle MNO to undergo a shear factor -3 with the line y is equal to 0 invariant. So this time the x-axis is the invariant line. We start with point M. Perpendicular distance from the invariant line is 3 units. S is -3, so displacement will be equal to -3 times 3, which is -9. That is 9 units to the left. M prime is here. Point N. Perpendicular distance from the invariant line is 1 unit. S is the same -3, and so displacement is -3 times 1, which is -3. So we move 3 units leftwards. So N prime is here. Lastly, point O. Perpendicular distance is 2 units. Shear factor is -3. Displacement is -3 times 2, which is -6. So we move 6 units leftwards. And O prime is here. We join all the 3 points, This is our new triangle as a product of the shear process. Shear transformations parallel to the y-axis work in a similar manner. Consider triangle ABC to undergo a shear by shear factor -4 with the line x is equal to 3 being invariant. Point A. Perpendicular distance from the invariant line is 2 units. S is -4 and displacement is -4 times 2, which is -8. So we move 8 units downwards. A prime is here. Point B. Perpendicular distance from the invariant line is 1 unit. S is -4 and displacement is -4 times 1, giving us -4. So we move 4 units downwards and B prime is here. Finally, point C. Perpendicular distance is 3 units. S is -4, displacement is equal to -4 times 3, which is -12. So we move 12 units downwards. C prime is here. If we join all the 3 points, the transformed figure is A prime, B prime, C prime. Now,